In this work we present Mighty, a multifunctional suction cup for object gripping and surface attachment. Mighty is a smart suction cup capable of force-torque sensing, as well as seamless attachment on any surface despite its roughness. The system consists of the smart suction cup, two solenoid valves controlled by the board to seal or break the created vacuum, an electronics board that holds the processing unit and the employed pressure sensors, a vacuum pump used to pump out the air from the suction cup, and the necessary auxiliary tubings for pressure readings. The smart suction cup is composed by four main parts: a compliant silicone cup, a plastic fastener, a plastic rigid base, and an inertia measurement unit base attached to the rigid base. In order to enhance the cup's robustness, a plastic inner grid is partially embedded inside the silicone, with the outer part serving as an anchoring structure while the plastic fastener is used to tightly secure it to the rigid base. For the silicone suction cup fabrication, a mold was fabricated. To achieve good adhesion on any surface regardless of its roughness, the silicone cup, in turn, consists of a combination of silicone rubbers of different hardness and plastics, with the softest silicone placed on its free surface. This multi-stiffness design enables the suction cup to seamlessly attach to the surfaces, while retaining its form. In order to convert the pressure reading of the embedded chambers and the suction cup to useful information, a calibration sequence must initially take place. In this calibration sequence, air is pumped out of the suction cup in steps, and measurements are taken of all pressure sensors. Given the measured pressure in the suction cup and its surface area, vacuum force is evaluated. Subsequently, we employ the above vacuum force to derive the chamber force for all chambers. The set of points is in turn converted to a continuous third-order function via a fitting procedure. After calibrating, we can use the acquired information to estimate the mean force of the suction cup as the average force measured by all chambers, which is employed to estimate any force applied to or exerted by the suction cup as the absolute difference between the vacuum force and the mean force. Chamber force estimations are also used to compute the torque applied. To achieve this, we first create P endpoints as an implied representation of the 3D location of each corner of the suction cup's frame, thus creating plane A defined by the corners while no external forces are applied. Plane B is defined by the new locations of the frame corners after a force has been applied, where Z location corresponds to the force applied to the chamber. The axis of rotation between planes A and B is given by the intersection of the two planes, with theta tau denoting the angle between the axis of rotation and the frame of the suction cup. The torque magnitude on each chamber is computed as the product of the force applied and the vertical distance of the chamber to the axis of rotation. The final torque estimate is derived as the mean torque of all four chambers. The ground truth of the torque is obtained via an IROS force gauge in combination with the inertia measurement unit. A series of experiments was conducted in order to assess the performance of Mighty under varying conditions. In order to test gripping quality, a set of 8 test pieces was fabricated using sandpapers of different grit, attached on flat surfaces. The performance of the proposed suction cup is compared against that of 3 commonly used suction cups. The comparative results demonstrate the superior performance of Mighty. A second set of experiments was performed to evaluate the accuracy of the suction cup's estimation of various types of contact states. The contact state of the suction cup is divided into 4 categories based on pressure readings from all 4 chambers and the suction cup. No contact, contact, good contact, and attached, based on the pressure readings of all 5 sensors. Force estimation experiments were performed regarding force estimations during lifting and stepping, where an IROS force measurement unit was employed to obtain the ground truth forces. For both types of forces, Mighty managed to achieve impressive results with a mean square error between the ground truth and the estimation in the order of 0.2 Newton. A torque axis estimation experiment was performed to evaluate the performance of Mighty, where the ground truth was acquired by the inertia measurement unit located on the suction cup's rigid base. A representation of the acquired chamber readings along with the estimation of the axis of rotation and the angle based on the IMU readings can be seen on the figure below, with a mean square error in the order of 2.5 degrees. The final experiment performed regards the torque estimation, where the IROS force gauge and the onboard inertia measurement unit are used to obtain the ground truth. During the experiments, the suction cup managed to accurately estimate the applied torque with mean square error in the 4th decimal point. The research leading to these results has received partial funding from the European Community's Horizon Project REICOM.